It's great to meet all of you. My name is Richa Sirohi. As was said, I work at the NASA Jet Propulsion Lab in Pasadena, California. I'm an end-to-end information system engineer, and I'll get a little bit into what that means and what I work on. But today I'm going to talk about the mission I'm currently on, which is called Psyche. We call it a mission to a metal world, and you'll find out why. So this here is a picture of our campus down in Southern California. If you ever get the chance, I recommend taking a tour. You can see where we operate the spacecraft, build them, and so on. So a little bit about me. I did get an undergrad degree in mechanical engineering, and then I studied here in systems engineering. I'm an alum of this program. So if you have questions about how the program applies to your future, happy to talk about that. And I'm still a Cornell student. I'm doing engineering management part-time. As far as career goes, I've worked on a variety of different missions as an intern, and then when I came full-time, including Mars rover, which is these big, massive flagship mission, Maya, which was an aerosol mapping mission for Earth science. I worked on Cold Atom Lab, which is an instrument on the International Space Station, Europa Clipper, which is a mission that's going to go study the moon of Jupiter, Europa, which has a global ocean. I've also worked on mission proposals, pitching to NASA, should we go and study this for the moon? And currently I'm on Psyche. And here you can see a picture of the Mars rover, the duplicate that we use for testing over at our lab. And that's my family. Like Wes mentioned, I'm really passionate about outreach work. I'm really excited to be here today. These are some of my favorite talks, and I'll take a picture from today. I'll probably add it to this slide. I love giving back to the programs I came from, so I just really appreciate the department for having me. So a little bit about what JPL is. I'm sure you've all heard of NASA at some point or another, but NASA has many different centers. Different centers focus on different areas of work. Houston, they do a lot of human space exploration, for example. And JPL is known for its robotic space exploration. It was originally founded through Caltech. A bunch of the grad students, as you can see up here, were trying to make their own rocket fuel in the 20s and 30s and ended up blowing up part of their dorm. And instead of kicking them out of school, Caltech gave them a plot of land in northern Pasadena and said, go do your rocket testing there. And that was the birth of the Jet Propulsion Lab. They then continued to do various experiments and technology development for the Army, all the way through World War II. At that point, they began to pivot to do space exploration. If you remember, there was Sputnik. The first satellite ever put in space was done by Russia. And after that, the US wanted to respond. So they asked JPL to make Explorer 1, which is the picture in the middle there, which was the first US satellite, which was built and tested at JPL. That was actually the first scientific exploration of space. There was a Geiger counter in the nose cone, so we discovered the Van Allen radiation belts. And that really started the future of JPL. And our program is really dedicated towards scientific investigation and use of robotics and satellites in space. And so we no longer do propulsion or jets. It's a little bit of a misnomer. And you can see here, this is the mission control as it was in the 50s versus how it looks now. Generally the same idea, a lot of new technology. And I'm really proud of that upper corner picture because that's all the women who make space exploration possible at work. I'm really proud to be in that sea of people. It means a lot. So a little bit more about what JPL does. It's not just robotic exploration. We focus on a few areas, right? So we've done a lot of Mars exploration through the rovers. We do a lot of concept development. There are so many missions that are pitched that never get funded. We have to go through that process to find the best missions possible and to really round out our design. So we have this Mars Ascent vehicle, the concepts being worked on, so we can go and retrieve the samples that the most recent rover has collected and deposited on the surface. And it's a huge international undertaking. We also have various support roles for making things like our rover, right? We need a clean room. We need all technicians to put it together. We need all our test beds that duplicate the functionality, and so on and so forth. So, right, it's not just the engineering team. It really takes an entire town to put these, spacecraft together. We also have Earth Science. This is a mission called NISAR. We'll use synthetic aperture radar. It's a joint mission between the Indian Space Organization and NASA to study climate change and the changing effects on land masses. And so that's really exciting because we also do a lot of diplomatic intellectual exchange with different countries and collaborate on different projects like this. We have a star shade concept in the works. So the idea would be we could unravel and unfold this giant structure in space using concepts from origami. To then block out the sun and have a telescope maybe a mile and a half away that can then, look at a sun, but with the sun blocked out, you can see all the planets orbiting a sun. Not ours, right, but a different star. And so we could find exoplanets. So these are concepts in the works. We're making tech demos, slowly we're building up the technology so that one day we could fly a mission like that. And we operate the Deep Space Network. So this is the one from Goldstone. There are 3 Deep Space Network locations around the world. It's in Spain, in Australia, and in Southern California, all in the desert. And it's in those locations, both because they're our strategic partners and allies, but also because it allows us to have constant communication with spacecraft, no matter where they are in space in reference to Earth, as long as there isn't another planetary body in the way. And that's how we bring our data back from any spacecraft that is beyond Earth. So if you think about the moon landing, all of that data, one small step, all of that audio, that came through our Deep Space Network operated by JPL. So today I wanted to specifically talk about Psyche. Psyche is the mission I work on. This is not a real image. There is not an asteroid coming for us, but it is a cool depiction of maybe how this asteroid so far from Earth was initially formed at the very start of the solar system. So Psyche is a very unique asteroid. It is, like I said, it's sitting between Mars and Jupiter. It's primarily made of metal, at least that's what we think, because the images we have of it show that it's fairly shiny. It's made of silicon materials, rock materials, and a lot more metal than most asteroids are. So we think it could be the core of a once Earth-like planet. It could tell us how Earth was formed. It could tell us how different planets are formed, and we can go figure out whether this was a planet that just stopped developing, or if this was, the core, because the rest of the planet got bombarded by asteroids and broken away. So it's a really exciting targeted mission that we're doing. We have a couple instruments to help us achieve this. We have a magnetometer, so we can study the materials in it and the magnetic field. We have a multispectral imager. It's redundant. We have 2 of them. And we have a gamma ray and a neutron spectrometer. And all those do is they're able to, as we get closer, look at the actual materials on the surface, help us understand the topography. Really useful for the geology. We also have a tech demo. So this isn't crucial to the success of Psyche, but if it's successful, NASA can use this technology in future missions. It's a deep space optical comm. And what that means is instead of using that deep space network and those antennas, because those are in high demand, there's so many spacecraft, we could send back data and command the spacecraft using lasers. So that tech demo is we send and receive data from this location in Southern California. And so I'm very excited to see that. We're launching this year on August 1st. Very excited for that. It's all hands on deck, trying to get that spacecraft done and tested and ready to launch in Florida. It's going to arrive at 16 Psyche, the asteroid, in 2026. So that's a 3.5-year cruise. Earth, if you imagine, is about 1 astronomical unit from the sun. Psyche is about 3. And it's going to take us quite a bit to get there, right? If it takes 9 months to get to Mars, which we will fly by Mars first, it'll take us, another 2 years almost to get all the way to Psyche. Once we reach there, we'll have a 21-month orbit, and I'll talk about the science we're going to do when we get there. And it's a discovery class mission. So this looks like a big number, 850 million, but that's what we consider a mid-sized targeted mission. It's not one of our flagship missions, like say the Mars rover, that's well over $1 billion. This is much more constrained. We have higher risk, but very targeted science. And this is a fun picture. It's me standing next to the Psyche spacecraft being built at our facility. That was just a few months ago. It's actually all put together now. So Psyche was discovered in 1852 at the Naples Observatory. And 16 just means that it's the 16th minor planet in its order of discovery. That's how we name asteroids. This is the astronomer who discovered it. And this is the best picture we have of it till date. We really don't know what it looks like. We have some idea that, there's metal, we've gotten some measurements, but we're not gonna have a better idea until we get closer. So all the other images of Psyche you see are really artistic depictions based on our current calculations. Psyche's pretty big. It's about 140 miles across. Now, it's not a perfect sphere, but if you put it between Phoenix and Flagstaff, it would cover that whole distance in diameter, or the entire width of Massachusetts. So this is not a small body. Like I mentioned, we're launching this year. So that's coming up in August is our first launch period. If we don't make it then, there's a few opportunities, but it gets slimmer and slimmer as, Psyche moves farther and farther away from our trajectory. What we'll do first is we'll launch from Earth. We'll do our optical comm testing so that NASA can validate the technology. We'll do a Mars flyby that gives us a gravity assist. It means we don't need as much fuel to get to our destination. We're using the gravity and slingshotting further. And then as we get to Psyche, we'll have these 4 scientific phases in which we'll get more and more data and use different instruments as we get closer. So each of the orbits, you'll just get closer and closer to the Moon's surface. I did want to talk a little bit about how long it takes to put a mission like this together. There's years and years before the start of this timeline where scientists are talking about, oh, well, what about Psyche? What do our measurements tell us? Creating hypotheses, building a community of interest, thinking about the technology that would go into this, and building those relationships with JPL. When it gets selected for flight, it's already gone through multiple phases of proposal development. We've gone through the concept, we've figured out what technology we could use, who we're gonna partner with. JPL thinks it's a good idea, NASA thinks it's a good idea, then it goes and gets selected. So these are people's entire careers, especially scientists, that go into getting a mission like this funded and then developed and flown. We go through a formulation phase for a couple of years, and then we have to get approved by NASA to go further on our design review. And then after a few more years, subsystems start to get built, right? All of the different instruments get made, all the different pieces of the spacecraft get made, and in phase D, we put it together and we test the whole thing. And that's where we are right now. And it makes me a little nervous to see the "we are here" arrow so close to the launch arrow, but that's how it goes. It gets pretty hectic towards the end, because you can't delay a launch window to another planet, right? You'll see we'll do a Mars flyby, and then, like I said, there's a vast period of time before we actually reach Psyche. And when we get here, it's about 21 months of science orbits. People often ask me what happens after those science orbits. We'll essentially just continue to orbit. It'll just stay out there. If you look at Dawn, which is another mission to an asteroid, it did the same thing. The idea would be to just simply not crash it into a body of interest, either Psyche or any of the other asteroids of interest that have water, for example. That would be a concern in planetary protection. But yeah, generally, it stays out there. There's no real way to get rid of that spacecraft. So I mentioned some of the scientific objectives, but we really have distilled it to about 5 on the project, right? We want to know if it's a core. We want to know how old the surface is. Did more rocks come and grew onto it? Is it really old? Did it come to our solar system, or was it here from the founding of our solar system? Lots of open questions that we'll be able to answer. We want to know what it's made of exactly. We want to know how it was formed, under what conditions, and we want to characterize its surface, right? Get better imaging. Really, we want to not have an artistic image by the end of it. And as I mentioned on the orbits, as we get closer and closer, we'll understand more. So we start with our magnetic field measurements from a distance, and we'll continue to get those. But when we move into orbit B, we're starting to look at the surface. Okay, well, what does the surface look like? What does this bird's eye view like? And then we get even closer, and we understand the composition, right? We use our spectrometers. And then at the very closest orbit, we'll have gravity measurements on top of everything else. So it really tells us the full story over time. This is a view of the spacecraft. So it's actually quite big. It's about 1.5 humans tall and wide, if that gives you some perspective. This has all the solar arrays folded in, and I'll show you what it looks like with it all folded out. But you can see we have a high gain antenna. That's how we send most of our data back and forth. We also have some low gain antennas. There's 3 that help us in backup, if you will, to send the extra data to make sure we get the commands. We have 2 of these cameras. If one fails, we have the other. We have magnetometers, same idea, they're redundant, and they're kept at a distance, right? Because we don't want the actual spacecraft bus to be impacting the measurements we're taking. We also have thrusters here to help us maneuver. We have our optical comm demo, that's the DSOC. And then we've got our spectrometers that are also sticking out a little bit so we get better, clearer measurements.
What was the approximate weight?
I don't have the weight. I think it's over a ton. I have to check.
Okay.
Yeah. This is the actual size. It's about the size of a singles tennis court once the solar panels are unfolded, and that happens in space. It's pretty cool because we're using solar electric propulsion, which is a little bit newer to NASA and really exciting technology. So it takes a long time to get there, but over time we're slowly accelerating more and more. And it's all just using solar power. So again, the instruments, we have our imagers to get geological compositional information, our magnetometer to understand, and also to help us, in the 3 dimensions, right? There's some of that data that's used in our navigation. And then GRNS identifies the elemental composition. And so one thing I want to highlight is this is really a joint effort across multiple institutions. Arizona State University, where our principal investigator is and where our science data center are, they're also providing the imager, right? So hardware comes from those places and those research labs. We have a magnetometer that's provided by both MIT and the Danish Technical University. And we have a gamma ray and spectrometer, and those are provided by Johns Hopkins Applied Physics Lab. And so this is, in many ways, an international and very academic partnership to make these spacecraft fly. So what I want to talk a little bit about today, especially because you guys are the systems program and systems students, is really how we do systems engineering on a project like this, and sort of what my day-to-day is like. So the end-to-end information system, That's a lot of words, and it's a very abstract concept. So I want to break it down a little bit. It's a set of functions. It's not a piece of hardware. It's actually a very abstract system. So it's not maybe something like you've learned in class where you have a product or a robot that does X, Y, Z. Rather, our system is defined by how it operates and what functions it can achieve. So when I care about what I do in my day-to-day as a discipline is I care about these 4 bullets, right? So I care about where data comes from, where it's going to be received and processed and needed. I think about QQCL, quality, quantity, continuity, and latency of the data. Is it going to get there in time? Am I going to get all the data? Am I missing pieces of the data, right? These are the things this is how I measure performance of my system. I care about how data is transformed over time. Where does it get packetized so that the next subsystem in the data flow can understand the data it's getting? And I'll break this down so it makes sense in context. And I care about operability. Can people actually fly the spacecraft? Does it make sense to them? Is it easier? Do the scientists actually get their data in a way that makes sense to them, that they can make informed decisions about what we're going to operate next? So those are the big questions I'm trying to answer. When you think about the end-to-end, the ends are very important, right? So the end is one end is everything that generates data. You have the spacecraft, you have the different instruments, and the other end are the actual users and scientists who then utilize that data to write papers, to complete their research, to validate their theories. So overall, the EIS is abstract, but once you implement it, once I test the full data flow, that makes it real. So it's made real through implementation and use. And so that's a very different perspective, I think, on systems engineering overall. So I work with a number of other disciplines as an EIS engineer because I don't own any piece of hardware in the data flow. I work with a lot of other teams to ensure that their pieces of hardware interface correctly and achieve the functions that I own, right? And so it's very cross-cut. These are the different areas I care about. So telemetry, which means all the data we're getting back, how we command it. Radiometric means just information about the spacecraft. Timing, making sure all the clocks on board are synced up, right? We don't want wrong time. Because we could lose track of where the spacecraft is if we have the wrong clock on board and doesn't sync up with what we have on the ground. I care a lot about how data is being compressed, right? If we have too much data trying to come down the pipe, it's going to get clogged. We have onboard networks, we have the ground data stations, we have how do we account for data? How do I double check to make sure I got all the data I was going to expect, right? If I didn't, how do I ask for that data again from the spacecraft? And does it make sense from the operator's perspective? What is their use case? What is flight like? What are they actually going to go do in space? Can I achieve those things? And so I support a number of things on the operations concept. I have to, JPL has a couple multi-mission services, right? The Deep Space Network. I can't go in and change how those antennas operate. I have to make sure that I interface correctly to those things. There's pieces of software that JPL wants me to use. And that means I don't have to spend money to develop that software as a project, and it buys down risk. But I have to also make sure that the project can accommodate those pieces of multi-mission services. So it's really interesting because we're not a standalone project. We have to build on the resources and the foundation of NASA and JPL. I also have to ensure that we have QQCL, right? So the way we evaluate the system, and that's the phase we're in now. Now the system's coming together, I'm testing for those 4 criteria. So when we go to design a system like this, keeping in mind how we're going to evaluate it and all the responsibilities I have as an EIS engineer and we have as an EIS team, is we have to look at heritage. A lot of things we simply inherit because they've been done before, they're a proven concept, we don't have to spend the money, time, and infrastructure on it, but it does complicate things because you have to make sure those old pieces of technology interface correctly with our new pieces of technology. So we have a lot of heritage from Dawn, which I said was another asteroid mission. We have a ground data system that we utilize, and then we have some key mission drivers. So we don't just have heritage, we have a budget that we are constrained to. We have a certain amount of risk we're constrained to. There's new software we have to accommodate and test for. Psyche is the first to accommodate this flight core product line that JPL is implementing. But when Psyche is successful, right, that's a risk reduction for future missions. So sometimes you have some of these internal drivers that have nothing really to do with the project itself, but the constraints around how you implement it. We also have deep space optical comm, which is really exciting, I think, to have these the capability to command via laser. But we have to make sure on the Psyche side that we're accommodating that piece of technology. Can we get data from DSOC? Can we ensure that it's operating correctly? And then it's a multi-org spacecraft, right? Whenever you're working with different teams, it's a very different set of ways of doing things, different processes for testing, different tools for testing. It gets complicated. You have to all make sure that you're on the same page about the fidelity of data you need, how the systems are going to be operated using all these different tools and achieving the goals of all these different teams, right, from the different universities. So it's definitely some of the challenges we have in implementation. Now, this is the highest level view I can give you of the end-to-end information system. We've got our data, we're uplinking from our ground station, we're commanding the spacecraft, we're looking at Psyche, we're collecting data, and we're sending it back. And I want you to keep this image in mind as I show you the next couple diagrams, just because it will get a little complicated. So this is actually the same picture, but it's showing you all the different interfaces between the teams. So here you have, the deep space network that's sending and receiving data between the spacecraft and between the ground. And on the ground side, you've all got all these scientists who say, this is the data I want to collect and learn about Psyche. Hey, mission system, can you help us command the spacecraft so we can achieve that? Can you help fly the spacecraft so we're in the right place at the right time? Is the spacecraft healthy? So they put together the sequences and send it up. And then on board, it gets executed through our avionics, which is basically the onboard computer. That's where our flight software is. That's where our bus interfaces are. So if you would know about networking and computers, that's where all that magic happens. And we have a lot of data coming in from subsystems. How hot is the spacecraft? How much power does it have? All the various sensors, as well as our science data from the instruments. And all of this gets sent back and forth. And then on the way down, it gets packetized in order of priority and then brought down in a way that's understandable on the ground. It gets unpackaged by the mission system, sent to the scientists and archived for all of humanity to look at, some 24 hours later. So this has to be a very well-oiled machine where we fully understand all the interfaces, right? How data is being changed, all the criteria I talked about. I like this little link right here, the dotted line, it's optical link. That's the future, right? When we can remove all of that and we just have a little dotted line, it'll make it so sleek. It'll allow deep space exploration, right? We'll have much faster communications times. It'll enable more human space travel to deeper space. Right now, even going to Mars is a challenge because sometimes it'll be hours before you can send data back and forth, right? So those are challenges that we're trying to solve through these growth in technology. Also, I wanted to point out, you take a model-based engineering class in systems, and this is one way to model a system, right? This is showing the direction of data flow and all the stakeholders in the system. So you understand who interfaces with who. There's a lot of detail also missing, right? All the ways in which these individual actors interact, all the different types of data being shared. There's a lot going on in the mission system and different roles and responsibilities, but this is one way to back out the conversation. A more detailed view is this. We're still looking at the same picture we were before, but here you have the ground system on the right and the flight system, our spacecraft, on the left. And this shows you in much more detail who is sharing exactly what type of information with each other. For example, the mission system through various services is providing images directly to the imager team. And then all of that gets archived. So it's showing you exactly what data we care about, who is requesting it, and how it gets transformed. And so this is what we call a functional view of our ground and flight system. Now, this is what we call a protocol stack. So what we were missing in the earlier diagram is exactly how the data is transformed over time to be understandable, right? All it was showing you is what data is transferred. This actually shows you how it gets transformed. So we have information coming in from imagers, from different instruments. They go through different bus interfaces. So they have to get interpreted by those computer elements. Then they get sent on board and they have to get wrapped up in a way that the ground can receive it, that big antenna I showed you. And on the ground, they get transformed again so that they can be sort of peeled apart. Imagine you put layers over the data so it can be sent safely in a way that we understand, right? Because you want to make sure that we've gotten all the data, has the timestamps on it, you put metadata on it, right? So all of that has to get unpacked in a way that is then understandable to the actual instrument teams. And so that's what we're showing you here. And I could show you even more detailed diagrams, but I think what I'm trying to get across is there's many different ways to model the same data flow, right? And we have to care about all the different ways in which we're talking about data. It's not just data goes from point A to point B, but it's how fast is it going, how much is going, how we received it all, how does it get transformed. So that's something I want you to take away is that you can look at the same problem multiple ways, and that's the best way of solving it sometimes. So a little bit about how we uplink data. People often ask me, well, how do you send commands? And so we have a couple different ways we send commands. We send immediate ones. Okay, we're connected to the spacecraft. We want you to do X, Y, Z, take these measurements. Sometimes we send sequences. So those we send up to the spacecraft and they live on board, and at some predetermined point of time, they start executing. So we know 4 weeks in advance, we're gonna get really close to Psyche and we want a bunch of images taken. Rather than try to time it at that right moment, there's a lot of risk, right? We send sequences in advance, especially when there's a series of events that need to occur. We also have command accountability. So we want to make sure that the commands actually sent. We don't want to send half a sequence. That could land us in a situation where the spacecraft is not quite collecting enough data or is collecting too much or is in standby. So we want to make sure our commands are sent accurately. There's also onboard functions and fault protection, we call it, so that if something goes wrong, if half a command is executed, if the thermal sensor is off, it'll go into what we call safe mode. So nothing's happening on the spacecraft. It's not going to fall out of orbit. We know exactly where it is. And on the ground, we can figure out what the problem is before telling it to, okay, you can go again. So there's a lot of complexity to this, but these are the main ways we command. On board, right, we have all this data that's being generated. So we call that telemetry every time you see the TLM. It's generated by the software, by all the sensors, and by our instruments. And it's stored in non-volatile memory, meaning we can go back and get it at any time. It's not going to just disappear. Real time is the data that's being continuously pushed. That's not stored in non-volatile. That's like sensors like, I'm hot, I'm hot, I'm hot, I'm cold, I'm cold. And it's just continuing to spit out data about the sensor. So we have a stream of that coming down, and then a stream of files in which that sometimes periodically we record that data so we can look at it later and kind of digest what's going on. And then we have, the flight software that handles all this and sends it to be cataloged for downlink. It doesn't compress our engineering or science data on Psyche, but some of the instruments internally do. So that's another interesting function of the data. The way we downlink it is where it gets interesting, right? So we have a data product catalog. It basically takes all the data products. It's like, okay, this is the priority. They told me to allot to you data product. You go in this order. Okay, you're number 3, you're number 1, so on and so forth. And we can reconfigure that data product catalog from the ground, meaning we can ask for different data priorities at any time, which makes the system highly configurable. But this also helps us not get jammed, right? We want certain data earlier. It helps us make informed decisions about what to do next. And this is how we go about asking for the correct data. It also helps because if we're trying to downlink and something happens with the ground station or the telecom system, we only get half the data, we can go back and request it again at the next pass. So it makes the system highly, highly robust, right? So it's retransmission. The data product catalog is stored in volatile memory. So if something safes or the computer has a blip and has to restart, we have to tell the spacecraft again what order we want the data down in. So there are some, challenges to operating the system in this way, but it's pretty robust and configurable, which is a plus for us. And then the way that's downlinked, you have this real-time data, right? That's constantly churning, and then you've got the recorded telemetry data products and the instrument data products that we all send for downlink. And I showed that protocol diagram. They have to follow certain protocols. Those are actually dictated by what we call the Consultative Committee of Space Data Systems. It's this international set of protocols that JPL helps work on that make sure that our deep space network can understand the data. And it's really a massive effort, right, to ensure that all these different space agencies are following these protocols in a way that allows our systems to interoperate. So it's a huge undertaking. Within that, we have a little bit of flexibility. How much do we want to check the data? How much cybersecurity do you want to add? Things like that. And so that's what we work on. But that's how data is downlinked through those protocols. And then one thing I want to highlight is that every data product has a unique identifier. We call it an application ID. And so it's based on this app ID that we can send it down by priority. And so that's how we're managing it. So I talked a little bit about how we evaluate the end-to-end information system, right? We want to ensure that we meet that QQCL, the quantity, quality, the latency. We also want to make sure that it's usable by our users. So we have a couple of features and challenges by which we've deemed Psyche is great for users as well as kind of a challenge. I mentioned sequencing and being able to load sequences well in advance. We're actually going to plan activities 4 weeks prior to them being executed on Psyche. That's a huge amount of leeway. Some projects you don't get that much. You get 12 hours, you get a day where you can load that in advance. So that's a huge advantage to our operations teams in flight. We also can downlink part of data products, right? We got half a data product, send me the other half. I don't have to request a whole chunk of data at once, which helps protect our downlink bandwidth. And we have a lot of onboard data storage. So if we don't get all the data down in real time, we can just go ask for it later when we're not collecting as much science data. Further, we have some challenges. If there's a bug in the code, we can't just update a portion of it. We have to update a large chunk of that flight software code, which takes a huge bandwidth on our uplink side, takes a lot of testing, right? You don't want to introduce 2 bugs and trying to fix one. So there's some challenges there. There's also portions, I mentioned safe mode. If something goes wrong, we go to safe mode. We only get 10 bits per second of downlink. That's so much smaller, right? We get hundreds of bits per second more nominally. And so that's a major challenge. And it means that we can also only use the smaller antennas. We can't use the larger we can only use the 70-meter antennas rather than the smaller ones. And the 70 meters are in high demand. So it's hard to get enough time on theirs to sort of troubleshoot. So major challenge there.
What's the normal bit rate?
It really depends on the state we're in. Sometimes it's 210 hertz, sometimes it's 360. So it just depends. Okay. But yeah, it's significantly higher than 10 bits, right? Yeah. And we're very choosy about what data we're going to bring down. We want power data, but we don't really need any instrument data, right? We want enough to be able to troubleshoot what happened. And because in safe mode, we have a low safe mode downlink rate, we have to be very efficient. We have to be very clear about what data we want and prioritize that in advance. Now, that's how we evaluate the system by how it's operated. We also have to evaluate it based on its architectural implementation. How well do we achieve those functions and how well are those interfaces implemented? And so we have some advantages. We have a single data center at the Arizona State University. That means all the scientists can pull their data directly from that one place. There's only one interface. They can get it extremely quickly, right? It's rapid. That's a huge advantage over other missions where it's been distributed. It can be hard for the scientists to get access to their data or to understand it. So this streamlines things quite a bit. It's also very configurable. Like I mentioned, we can tell it what data we want and what priority. That's huge for us. We have a lot of onboard storage. And we have that space and time partition flight software. And that's a new software that JPL wants us to test for the entire lab to use in the future. What it does is if one task is being greedy over time, it'll stop it, meaning we're avoiding that risk. And if one piece of software fails, it's partitioned. So only that piece failed, and we have some redundancy. It's great in theory. It is also on the challenges list because we have to test it, and it's new for us. And there's a massive hill to climb in that regard. We also have a hybrid flight system. That's a challenge, right? We have all these different people helping build the system, owning different components of it. It's not all internal to JPL, which makes it easier to work with your colleagues, right? You have to work with different institutions and processes. We also have a new ground data interface between the Deep Space Network. It used to be part of the Deep Space Network. Now they're putting it on the project side. So that's new for us to test as well. And each instrument I mentioned has a different bus interface. If you remember on the protocol diagram, means every instrument's data is being transformed in a different way before it gets to the spacecraft's computer. That's a massive challenge, right? In the past, it's sometimes gone through the same interface. So it adds a technical complexity to the system. And this is pretty much what I had for technical content, but I encourage you, if you're interested in Psyche, to follow it on social media, follow the principal investigator, get involved, watch the videos. There's tons of cool technical content out on the internet and cool creative projects as well. I like that we do a Psyche inspired program. There's students who are really interested in art and the communication of science through art. And so we help encourage students to submit art designs. There's an internship program for them, for college students. So that's some cool graphics that they made. And one piece of advice I want to leave you with, this is our JPL motto, is dare mighty things, and actually comes from a Theodore Roosevelt quote. And it's far better to dare mighty things than to live in the great twilight that knows neither victory nor defeat. And so it's not just about STEM or spacecraft engineering or, it's whatever you apply yourself to, right? Dare mighty things, give it a try, push yourself a little bit further. Otherwise, you'll kind of always be left wondering, what if I had done just a little bit more? And I love this picture. These are all our students who come in for the summer. They do research, our graduate students who collaborate. I point this out to be, to say when I was looking at NASA, I just thought, oh, I could never do that. But there are stages, right? You can do that. People will teach you if you put yourself out there. That pipeline does exist, right? So imagine yourself there. Imagine yourself successful, and those paths will appear. Yeah, so some advice. These are the references for today's presentation. If you want to dig deeper, I can send these to you. These are some of my publications. I included my 2 from JPL as well as my 2 here in Dr. Green's lab in robotics. Love that. And this is my personal information. If you want to check out some of my work on my website, connect with me on LinkedIn, please do. It's been an absolute pleasure talking to all of you today. I really wanted to emphasize that I want to answer questions. So I wanted to open the floor at this time to any and all questions you guys have, either about Psyche, JPL, or my own journey. Thank you guys so much.
Questions? Got plenty of time, I think.
Yep.
Sure, question. Hi, Richa. That was fantastic.
Oh yeah, thank you.
And you have a way of doing it so economically. There's a lot. You offered us a lot in a short time. But you talked at the end about this new software kind of strategy, which dealt with this sort of greediness,
Space
right?
and time.
And so could you talk a little bit, as much as you can, about, is the culture of JPL a little bit accommodating this sort of new approach, which seems to be dealing with unexpected, right, as will inevitably occur. The unexpected is now of course we have all these means that we're kind of stumbling through, but trying to implement in the way of whatever intelligence, machine learning, and all the rest. Is that becoming more part of this? So like kind of a little bit more of a bottoms up?
Yeah, a little bit, right? But we're taking it piecemeal. So when you're dealing with such a complex system, you rely a lot on the heritage of what came before, right? So we can't overturn every piece of technology and use the biggest and brightest thing because we don't have the money, we don't have the time, we don't have the resources. But the idea of, if we can better one area, say the software, so that future missions will also benefit, NASA tends to put a high value on that, right? Let's invest the time and resources and do it right, and then it becomes standard for everyone else. In the case of this flight software, there's a good culture around working it bottoms up. It is exciting, right? We need good flight software talent, we need good software engineers, and we're competing against some of these big tech companies. So offering work in new exciting technological developments is one way. We retain that talent and build that talent. There's artificial intelligence being used on the newest Mars rover. It can drive around and it can say, hey, this is interesting all on its own, and take scientific measurements to some degree and optimize its time so it's not dependent on people on the ground. In our case on Psyche, we're using optical communications. That's new. We're using this new flight software. So there's a good culture around it. It is just really tough to test. There is a high responsibility for risk reduction, especially when you're talking about these publicly funded missions, right? Because there is high publicity on failure. That isn't to say that we haven't failed. Every space agency fails quite a bit in the beginning, and we fail as a team, right? No one is singularly responsible. But there is just extensive amounts of testing that has to be done, extensive amounts of documentation. And there are just so many people involved, all these different agencies, companies, that we have to have a shared understanding. So those are where the challenges lie. That's what makes it feel somewhat bureaucratic in a way compared to some of the more entrepreneurial ventures. But that's how we have to build, right? We're not just building one mission, we're building the entire space agency program over time. So it's twofold. Yeah. It's a great question. Yeah.
You want to check online to see there's 8 participants there. There's a chat. Jake, can they ask questions? I don't know if Jake can hear us or not.
Yeah, I see some questions in the chat that appear. So there's a question on how we use lasers for communication. Yeah, that's a great question. A lot of that technology has been developed by MIT. I would recommend looking up optical communications MIT. There's tons of papers on it. There are a lot of the protocols and the technology behind it that haven't been released. And so I want to walk the fine line of not speaking to things I shouldn't. But what we have is we have a ground laser transmitter and a ground laser receiver. There's 2 different locations in Southern California. And so what we'll do in cruise, which is what we call a period of time as we're trying to get to Psyche, we're not taking a lot of scientific measurements. So, let DSOC have its moment. So when we're a little bit far from Earth, we're not quite to Mars, we'll turn the spacecraft so the DSOC is pointing at Southern California, and we'll practice receiving commands, seeing if we can send that data to Psyche, get a response, and send Psyche's data back down via this optical comm. And it should happen pretty much rapidly. We can send high quantities of data quite fast, right, at the speed of light. So it's really a transformative piece of technology. It's the first time NASA's doing this in flight, but it's not the first time it's happening in industry. I think about a year or 2 ago, SpaceX tried it. So it exists out there, but this is pretty new in the past decade, I would say. It's at the forefront.
I have a question.
Do they simulate any of this stuff? Simulation, especially in data.
Yes.
You could set up some kind of a simulation model in scenarios.
Yeah, so we have what we call test beds. So if you look at it, it just looks like computers. It looks like a giant metal rack filled with computer servers, and you see the lights blinking. But all of that is simulating what is actually happening in flight on the spacecraft, how we send data, it has fake sensors, right? So when we do a testing program, first we simulate just on a computer, just simulating it there. We run our procedure, our command send correctly. Okay, great. Then we take it to a test bed where they have more robust simulations. And in some cases, they actually have models. So the same imager that's in flight, we have a version of it on the test bed that is not of high fidelity. It's not cleaned up. It's not put in the right configuration, but it's close enough that it'll produce pretty accurate data for us to test and bring down. And so and then we take it to what we call ATLA, which is our assembly, test, and launch operations facility. And that's that clean room I showed you. Everyone's in the big bunny suit, the air is regulated, humidity is regulated, and we actually test on there. But only after you've gone through like multiple series of testing on simulation are you allowed to test on something that's going to actually fly, because the risk is extremely high. If something breaks, if something is fatal, right? You also want to figure out, though, if something's wrong on the spacecraft, so you do need to test on it. And that's that back and forth of how much risk do we take on, what tests are safe to do. Recently, we just did our TVAC test. So it's the thermal vacuum test. We take our giant spacecraft, right, the one that size of a tennis court, we stick it in a room where we've controlled the temperature, and we make it as hot as it'll experience when it's in direct visual of the sun, and I'll make it extremely cool as it will be near Psyche, and see if it can withstand all of that. And now we're going into dynamics testing, and we're going to basically put it on a giant table and shake it really hard and see if it can withstand launch.
Shake and bake.
Yep. It is called, it's just shake and bake. Yep. So lots of testing that happens, simulation work, hardware work, multiple levels of it.
So much testing.
So much testing. About the last 2 to 3 years, it's just testing.
Better now than later.
Exactly. Yeah, I'd rather know.
Ahmed has a question there about laser and clouds.
Oh yeah, so all our science data systems, the science data center that I talked about, where all that data is accessible from the public, from scientists, all of that's on the cloud. So we use Amazon Web Services. That's public knowledge. They have a whole advertisement about how they've helped the Curiosity and Perseverance rovers. But yeah, so it's on the cloud.
He was talking about clouds and lasers.
Oh.
I don't know. That's my guess, but
yeah. So there is minimal weather impact, but that is part of why they've chosen Southern California with
so sunny there.
So sunny, cloudless. That there's some impact there. My bad. I thought you meant the other cloud.
The cloud.
The cloud. How would you simulate and test a newly fabricated system versus shelf components? That's a great question. So obviously new technology has to be tested more rigorously. If you look up the NASA technology readiness levels, it has to go through years of development before it can even fly. So you develop a concept, you prototype it, you prove it on the ground. Then when you reach TRL of 5 or 6, you want to see it in flight. So like DSOC is going to fly on Psyche, but it's not crucial to the mission. Right, but if we prove it, it gains a higher technology readiness level and it can be used on spacecraft. So every piece of technology has this sort of label to it. Even pieces of flight software, has this been done before? Is this checked enough? If it's new flight software, it goes to far more rigorous testing. You're right about that. So
yeah, reuse can be very scary.
Yeah. It still gets tested. We don't trust anything face value.
Yeah. Question here.
Yeah.
So I had a question. I interned at JPL like 2 summers ago. And I did some like really early stage like conceptual architecture stuff for MSR, and then I helped with B&B for 2020. And I was like, I guess my experience in seeing like the 2 different approaches to systems engineering, like early in the process versus late in the process, were really different. So I was wondering if you could elaborate on that, if that's something that you see on like the data side as well, and if there's like a difference between sort of conceptual architecture and then focusing a lot on documentation.
Yeah, no, those are great questions. So earlier, like before the flight's even selected, it's really just very entrepreneurial. Oh yeah, we can use this company's, this instrument, we'll grab this from here. No one's really talking about interfaces. They're really trying to rapidly size how much risk is this going to be, how many people are going to need, how much time is it going to take on a very, very high level. When you start to get into the actual development of the concept, you start to realize, oh, we can't build everything from scratch, or oh, this technology is not ready, we'll have to use something old. So in the data flow, we often don't come in until sort of mid-phase. And when we come in, some parts of the system are fully, like they're in place, We're gonna use this from Heritage, this is old, these are the instruments. So we just inherit these interfaces. We just have to accommodate them. We don't really get a choice. And then there's a lot of things on the flight software side that we have to be knowledgeable about in advance. We use a lot of lessons learned from past missions. From then on, it's all about risk reduction and improving functionality. So it's not so much this entrepreneurial, how can we implement new technologies, it's how do we make this more robust? How do we test in time? Do all the data flows work? Do all my functions work accurately? Very, very different mindsets. And so, you know, we have people who can do both, and I've really enjoyed doing both. But we have people who really just like to test. We have some people who really just like to develop the concept and document it. I will say it gets harder to document in later phases. So in the beginning, you're like, this is what I've designed, here's a document. And then later, oh, this doesn't work. Oh, we've changed the flight software there, but it's happening faster than we can write it down. And so we document these changes in sort of tickets in real time, but sometimes it doesn't make it into our larger documentation, our manuals, things like that until after it launches. And that's just the name of the game.
Brianna wants to know about chips shortages. Any logistics issues? It's probably, you got everything built.
Well, we've been impacted by COVID in a lot of ways. We haven't been impacted by chip shortages because they're sort of specially made. For a lot of these, they have to be radiation hard. That's a whole different pathway than your normal commercial chips for technology. That is, it has impacted some of the cheaper CubeSats that do use just off-the-shelf technology like that. So I have heard about that. We've just been impacted by like personnel shortages, various aerospace companies going under through the economic times, right? So some of our suppliers just we didn't have a supplier anymore. And it's not just impacting, right, Psyche, but the entire lab. And so missions are taking longer. We've had, it's been pretty detrimental across the industry. That being said, aerospace is booming, right? So there's new startups every day, there's new launch vehicles. So it's sort of this push and pull of, but it's tough, right? Because you have these new companies, they haven't bought down risk, they haven't proven success. It's just a very interesting time.
TRLs.
The TRLs.
Really low.
Yep. So we have sort of volatile supply chains, if that makes sense. Not particularly with chips, but overall.
So they just coat everything with aluminum foil Reynolds wrap, you know?
well, it depends. So it's when I talk about radiation, for example, Jupiter has a lot more radiation than say Psyche will. And so at Jupiter, we have to put the computer surrounded by tungsten metal, which is super heavy, takes so much mass, but it has to be in there. Otherwise it's going to fry after just a few months, right? We're not going to get any data. So it's an interesting problem. We have entire teams who work on that as well. I want to make sure I didn't miss any questions.
Chat's working pretty good.
Great.
Okay.
Any other questions? Anything at all?
What about virtual machines? Are you guys using, you talked about having this, ability to do updates and test, and are they using virtual machines?
Yeah. So we use virtual
Quite a
machines.
technology now.
Yep. For our testing of our basic procedures, that's on a virtual machine. I could remotely log into our test bed from here and test my tests from wherever I am. That was an accommodation we made in the pandemic so that people could test on some of the engineering models and those test bed racks and simulations remotely.
Yeah.
So we've done quite a bit of things to try to keep it all moving. But yeah, virtual machines are huge.
Are they going to use them on the satellite?
We have what we call like a mission support area, and that has direct connectivity, right? There's specific computers that have access to send commands, right? That's all very different.
Right.
Different machine.
Higher, different reliability.
Yeah, very high
iOS.
reliability. Yeah. Yep. Yes.
Yeah, I actually have questions about like the lifetime of the spacecraft.
Yeah.
Are you like having a mission to also bring them back in order to like?
Yeah, that's a great question. I get this question quite a bit. Is like, are we going to bring back samples from Psyche? Are we going to bring the spacecraft back? And honestly, no. Right? If you look at the past Mars rovers that have died, they're sitting on Mars. There's nowhere for it to go. It won't decompose. They're just out there. Some missions, like we had a Cassini mission, it orbited Saturn. The end of life for that, because we didn't want it to get pulled into orbit for a moon and crash onto a moon because they're of interest to us, we purposefully drove it into Saturn and burned it. That was just the best thing to do. We were running out of fuel. Why let it fly out there, right? We have the Voyager spacecraft. Those were launched during the Nixon era. We have 2 of them. And so they're actually beyond our solar system. They're the farthest things from Earth. We still get data through those antennas I showed you. There's only a few instruments alive on it, but it's going. And when we lose contact, it'll just be out there. We will never know. Very fascinating, but yeah. There are efforts to bring things back though. JAXA, the Japanese Space Agency, is the only one who has successfully brought back a sample from an asteroid. It's the Hayabusa mission, if you're interested in looking at that. And then we're doing Mars sample return, as you mentioned. So Mars 2020 is collecting soil samples in these little tubes and depositing them on the surface of Mars. And we have a joint effort with the European Space Agency, with Goddard Space Center, to go and send a lander. There will be a fetch rover. It'll go collect the samples. We'll develop something on Mars 2020 is taking the CO2 and developing breathable oxygen to test that for astronauts and liquid oxygen to use as fuel propellant. So we'll make our own fuel on the surface of Mars. We'll launch that rocket with the samples into space. We'll have an orbiter that will collect the samples from the rocket in space. It'll fly it back to Earth. And we have something else that'll bring it down into Arizona. We'll crash in Arizona. We'll take the samples into a special containment unit and study them at this facility so we don't contaminate Earth with anything from Mars, vice versa. We have planetary protection that works on that. And that'll take, well over a decade. So yeah, we will bring something back. It'll be exciting. It'll be in our lifetime, but yeah.
Maybe yours.
10 years. Yeah. That's a great question.
Well, thank you very much.
All right.
I appreciate it, Richa.
Thank you.